make a up-down segment here and a left-right one there, and it looks like a cross, especially if you delete that segment and that one there. It looks very much like a cross. So anyway, Deneb is a pretty bright star in Cygnus, the swan, or the Northern Cross. And then down here, Altair in Aquila, the eagle, is a bright star. And this is known as the Summer Triangle. Well, Vega is a star that has a dusty disk of gas still circling it. So there's a star, Vega. It's a pretty young star, but it's still got a lot of gas and dust circling it. And we think that that gas and dust has recently formed planets and may still be forming planets. And indeed, some astronomers claim that they have good evidence for a planet twice the size of Jupiter in the dusty disk of Vega, the brightest star of the Summer Triangle. Well, some of the stars, the so-called stars that you see in the sky, are actually planets. And you can tell because they move around from night to night relative to the other stars. You know, the Big Dipper doesn't change its appearance from night to night. It may rotate across the sky, but the separation and physical spacing of the stars in the Big Dipper don't change. But when you have a planet, it wanders across the sky and its physical separation from other stars changes or appears to change. And here, for example, is Jupiter, which is near a cluster of stars at this moment, the Seven Sisters, or the Pleiades. A few nights later, Jupiter will have moved to a different part of the sky, a slightly different part of the sky, so the orientation will change. And the planets, indeed, are the wanderers. Planet means wanderer in Greek, and the Greeks noticed that some stars appear to wander across the sky and are unlike normal stars, and the patterns change with time. I like photographing the planets and the moon. Sometimes you can get some really striking configurations. Here's the crescent moon with Venus, Saturn, and Jupiter, all in a relatively small angular area of the sky. It was a very pretty sight just before morning twilight. And here's another one in evening twilight where Venus, the bright one, and Jupiter, still quite bright, but not as bright as Venus, were very, very close together in the sky, about the separation equal to the diameter of the full moon. So it was really a striking sight, and these kinds of sights are really wonderful. Indeed, when Venus is close to the moon, astronomers at observatories tend to get a lot of phone calls from the general public claiming that there's a UFO in the sky, because, you know, Venus close to the crescent moon is a really striking sight. People notice it, and they call us up and they say, hey, there's a spacecraft rushing toward us. And we're all, no, it's just Venus, it's just Venus. And they're all, no, we're sure it's a UFO. And we tell them, well, just look tomorrow night. The spacing between Venus and the moon will have changed, but Venus will still basically be there and won't be any closer to us or whatever. Anyway, so it's kind of fun. Now here's a nice grouping where you have Mercury, Venus, Saturn, and Mars all quite close together in the sky. So it's fun to look at planets like this and how they wander across the sky. Now, what if you're looking at a bright star and you think, gee, that doesn't quite look like it's in the right place. That doesn't fit any of the constellations I know. Well, indeed, you might be confused by the presence of a planet. You can try to verify this by looking at how much the object twinkles. It turns out planets twinkle less than stars in general. So let's consider what causes twinkling. Here is an image of a star dragged across the field of view, and you can see that its apparent brightness is changing. It is twinkling. What causes that? Well, our atmosphere is turbulent. It contains many layers of air having different temperatures and densities and stuff, and as the light from a star hits the atmosphere, it gets bent or refracted. We've already discussed that in the first few lectures. And because the atmosphere is always changing with time, the amount of bending is changing as well. So sometimes a lot of light is hitting your eye, and then a moment later, most of that light may have been deflected by the atmosphere to someone else's eye, or the ear next to your eye, or something like that. That is, the rays of light hitting your eye are variable in time because of the variations in the bending by the atmosphere. And the effect is really quite similar to what you see at the shoreline of the ocean when you go into the shallow water here and you look at the sandy bottom. You can see bright spots and darker regions. Now suppose your eye were right there at this moment. Looking up, your eye would see a bright sun, But a moment later, this bright ridge would move over to here, let's say, and this dark spot would move over to where your eye is, and so the sun would appear darker. And then a moment later, some other little thing would move past your eye, and you would see a brighter sun. So these are little images of the sun on the sandy bottom below. And if you were looking up from the bottom, you would see the sun varying in brightness because of the rippling effect of the water, analogous to the rippling effect caused by the Earth's atmosphere. And you see this quite well at the bottom of a swimming pool. If you look at the bottom of the swimming pool, you can see these alternately bright and dark regions as the water concentrates the light rays in some areas, such as this, at the expense of other areas like that one there. I mean, the total amount of light has to be constant, but it gets concentrated in different regions at the bottom of the pool because of the rippling effect of the water. Now, the rippling effect of the water here is quite strong, and I show this particular image to illustrate what happens when you're looking close to the horizon in the sky. When you're looking close to the horizon, your line of sight is peering through a lot more atmosphere than when you're looking straight up. We discussed that in the previous lecture when considering the blue sky and the red sunsets, okay? So when you're looking through a long path in the atmosphere, there's more different layers all moving around, causing this bending of light to and fro, and the twinkling effect is enhanced, all right? When the star is high in the sky, the twinkling is sort of muted because you're not looking through as much atmosphere. So when you're looking close to the horizon, stars and even planets twinkle a lot more than when they're high in the sky. But I mentioned a few moments ago that planets don't twinkle as much as stars do in general. And here's an example of that. There's the star whose path across the sky I showed a few minutes ago. And there's a planet, Jupiter. And you can see that its light is much more constant than that of the star. Now you've got to be sure to compare a star and a planet the same altitude above the horizon, precisely because of this effect that I just mentioned, that if you're close to the horizon, a planet can twinkle just as much as a star straight overhead because of the larger amount of atmosphere that you're looking through. But if you compare two star-like objects at the same altitude above the horizon, and one is twinkling a lot and the other is not twinkling much, that other one is likely to be a planet. And here's the reason. Stars look like points of light, even through a telescope. I mean, stars are giant things. They're giant suns, but they're so far away that they are just little points of light. Planets are physically smaller than stars, but they're a lot closer to us. So through a telescope, you can tell that a planet consists of a disk. Here is an image of the planet Jupiter. It consists of a clear disk, much bigger than a star. I mean, here's a moon of Jupiter. Even that looks bigger than a star would. I think that might be a star down there, this little tiny speck, okay? So planets appear as disks. Even though every point on the planet is twinkling, some points will be twinkling brighter, others fainter at any given moment. And if you have many, many points across a disk, 1,000 points of light, say, the twinkling tends to average out. Some will be twinkling high, some low, and the whole thing averages out. So when you're looking at this thing with the naked eye, and you can't tell that it's a disk, all these points of light have merged together, and the average stays roughly constant. And that's why planets twinkle less than stars do. So here you can see a diagram of this effect. A star looks like just a little point. A planet is many points. Each of those points is twinkling, but the twinkling tends to average out because some are bright while others are faint. And when you have 1,000 points of light, the whole thing sort of averages out. Look at the planets that are in this photograph, for example. All of them twinkle. Now you can't tell that because this isn't a time-lapse photograph, but when I was looking at this, I could tell, for example, that that one is a planet, that's Mars, and that thing is a star, because Mars was twinkling a lot less than the star was, and yet they're about the same altitude above the horizon. And the twinkling is most easily seen for brighter stars, so you'd expect something this bright to be twinkling a lot if it were this close to the horizon. but it wasn't twinkling very much at all, and that's a dead giveaway that that bright thing is Venus. A really bright star in the sky that isn't twinkling while the other stars that you see are twinkling a lot, that's really likely to be Venus or Jupiter. Okay, I mean, Jupiter gets to be quite bright as well, but if it's close to the horizon, it's likely to be Venus. Now, when Sirius, a very bright star, is really close to the horizon, it twinkles in a way where you can even see colors. So here's a color photograph of the same view that I showed earlier. Here's Sirius twinkling, and you can see that the color is changing with time. And the reason for that is that, as I discussed when I talked about the green flash, a sun or a star in the sky that's close to the horizon has its light bent or refracted, and different colors are bent by different amounts. So in the case of the sun or Sirius, the true position might be down here, but the red, green, and blue images will be displaced upwards because of this bending or refractive effect. Each of these then forms its own individual image of Sirius, and they twinkle independently. So while the red image might be bright at any given moment, the green one and the blue one might be faint. And then the next instant of time, maybe the blue one will be bright, and the red one will be faint, and maybe the green one will be in between, and then the green one will be bright. And so you can see that if different parts twinkle independently, a particular color may dominate at any given instant of time, and that's what causes that effect. And you don't have to have Sirius be below the true horizon for this to happen. It can actually be up here somewhere, and its image is still refracted up, not as much as in this case, because the higher up the star is to begin with, the less bending there is. But in any case, anytime Sirius is pretty close to the horizon, you get this effect to some degree, and the twinkling can be chromatic or dependent on color. Another easily visible thing is the phases of the moon, and I'll be discussing the phases of the moon in much greater detail in Lecture 9, but here you can see the various phases of the moon, and it's just fun to monitor them. It takes a month for the moon to go through its full set of phases. Indeed, the word month comes from the word moon, okay, and the lunar cycle. Bright meteors or shooting stars can also be seen, and I'll discuss those in a lot more detail as well. But here is a shooting star, a streak of light through the sky, and it's not a star at all. It's just a small grain of sand pummeling through our atmosphere, heating up due to friction and burning up. Here's another one, which happened to be over a particularly calm lake, and you can see its reflection and the reflection of the stars in that lake. I love that photograph. You can also see satellites in the sky, such as the International Space Station. Here it is, streaking across the sky in a time exposure next to the lunar halo. There are lots of satellites up there. Here's a telescopic view of the International Space Station. You can see it's not just a point, it's a fairly complex structure. And you know, occasionally these things appear to streak across the sky and cause a bright flash. And that's especially the case for a set of satellites known as the Iridium satellites. There's about 70 of them. They're communications satellites, but they're not used very much these days. But they have these bright reflective panels, and at certain angles, these reflective panels can reflect the light of the sun toward you, causing a bright flash that lasts for just a few seconds. And here you can see a photograph of these bright panels. It's easy to confuse an iridium flare of this sort with a bright meteor because, you know, there are flashes of light in the sky. But if you see one near sunrise or sunset, it could well be a satellite reflection. If instead you see one around midnight or late into the night, it can't be a satellite reflection because the satellites are in low Earth orbit and only see the sun shortly after sunset or before sunrise. And so, you know, you can confuse these things with meteors, but not at certain times of the night. So I hope this shows you that there's lots of cool, bright things that you can see with the unaided eye in the sky. Go out and look and enjoy the splendor of the heavens.